Hello, welcome to my talk. Today's topic is on turbulence modeling, two-equation turbulence models. Part 1, conventional turbulence models. In this talk, the basic two-equation turbulence models will be introduced, including the popular K-epsilon and the K-omega turbulence models, as well as the less popular KL, and K-tau models. In this talk, I will introduce how these equations are derived and approximated, and the examples are given for some basic flows. In the summary, the advantages and disadvantages for K-epsilon and K-omega models are discussed. In this talk, I will introduce the fundamental equations for two-equation turbulence models, including Reynolds averaged Navier-Stokes equation and the Bose-Niska's hypothesis, the turbulence transport equation for turbulent kinetic energy and the dissipation rate, the introduction of the Selfman's generalized transport equation, and then the introduction for K-epsilon two-equation turbulence models, the K-omega two-equation turbulence model, and other two-equation turbulence models, applications of the turbulence models to the simple flows, the concluding remarks, the advantages and disadvantages of K-epsilon and the K-omega turbulence models. For the turbulent flows, the dynamic equation is the Reynolds averaged Navier-Stokes equation, given by this. Here, the capital letters, capital UI, capital UJ, and capital P represent the averaged velocity and the pressure in the turbulent flows, and the specific Reynolds stress tensor tau ij given by this. This is a symmetrical tensor introducing 6 unknowns to the Reynolds averaged Navier-Stokes equation, and the question is that we have no more laws for building equation for solving these unknowns. For the turbulent flow, the Reynolds stresses contain all the information of the flow turbulence. So according to Wilcox, Reynolds averaging is a brutal simplification that loses much of the information contained in the Navier-Stokes equation. So for turbulence models, it is of vital importance how we can effectively model or retrieve the flow turbulence. So to close the Reynolds averaged Navier-Stokes equation, the Bose-Niska's hypothesis is often used, as we see in the 0, 1, and 2 equation turbulence models. Using this relation, the Reynolds stress is linked with the mean velocity, capital UI and capital UJ here, and the turbulence kinetic energy K here, and the nu T here is the turbulence eddy viscosity. For incompressible flow, we can calculate tau II as this, and we can see from the continuity equation for the incompressible flows, these two terms will be 0. Therefore, we have the expression as this. So tau II equals 2 minus 2k. So substitute the Bose-Niska's hypothesis to the Nernst equation. We have the Reynolds averaged Navier-Stokes equation expressed as this. So to solve this equation, the key issue is to determine the turbulence-related parameters K and nu T. So in this talk, we will see how we can use the two equation turbulence models to close the dynamic equation for turbulence flows. As we have shown, the transport equation for Reynolds stresses tau ij can be derived directly from the Navier-Stokes equation given as this. So in this equation, we can see the production term and the viscous term, which can be calculated if the mean flow and Reynolds stresses are solved. However, we have also some other complicated terms. The pressure strain term given by this, which would introduce 6 unknowns. The diffusion term Cijk given by this, which introduces 10 unknowns. The dissipation term epsilon ij given by this, with 6 new unknowns. Therefore, we build this transport equation for solving the Reynolds stresses tau ij of 6 unknowns. But unfortunately, we introduce 22 new unknowns. For simplified turbulence models, we are not solving the Reynolds stresses directly. Instead, we solve for the turbulence kinetic energy K, and the corresponding transport equation can be derived if we take I equals to J. For the incompressible flow, we have the equation as this. In the derivation, we use the expression for this and consider the incompressible flow. All these 4 terms are 0. Now we turn the relevant terms using the Roman numerals 2, 3, and 4. These terms are corresponding to the region in the figure of the energy cascading process in the turbulence flows. In the region 2, the production term represents the interaction between the mean flow and the turbulence, which extract energy from the mean flow and deliver the energy to the eddies. The region 3 is the diffusion region, involving some double and triple correlation. This term represents the transport process of energy from the large eddies to the smaller eddies. And the region 4 is the dissipation term, including the viscous term and the dissipation rate. Based on the DNS data, the diffusion term is small for some simple flow. Thus, it can be simplified using the diffusivity approximation in this equation, which is widely accepted in most turbulence models. So from this equation, nu T is the eddy viscosity. Therefore, this relation implies that the diffusion process can be represented with the eddy viscosity. So, we can obtain the transport equation for the turbulence kinetic energy given in this form. This is the most used transport equation for turbulence kinetic energy. So, to close this equation, the dissipation rate epsilon and the eddy viscosity coefficient nu T must be specified or solved. In turbulence flows, since the dissipation happens in the very small length scales. Thus, it is generally accepted an isotropic relation for the dissipation rate given as this. And if we take I equals to j, we have this. And the dissipation rate epsilon is given by this formula. And the exactly transport equation for the dissipation rate epsilon is derived as this. From this equation, we can see the transport equation for the dissipation rate is very complicated, especially in this large ellipse, which involves various complicated double and triple correlations, and these terms must be modeled. One big question is how we can best model these terms. So it should be noted this transport equation for the dissipation rate is solved only for the K-epsilon 2 equation models, while in other 2 equation turbulence models, for instance, the K-epsilon model, the transport equation for the frequency omega would be proposed based on the physical reasoning, not derived directly from the Navier-Stokes equation. The transport equation for the turbulent kinetic energy is given as this, and the corresponding transport equation is given as this. Now we can look at these 2 equations. We can see the similarities between these 2 transport equations. Term 1 represents the local change of the turbulence kinetic energy and the dissipation rate. Term 2 is the convective term for these 2 parameters. And term 3 is the production terms for these 2 parameters. Term 4 is the viscous terms. And the other terms in the green ellipses. These 2 terms are very complicated, which must be modeled in the turbulence modeling. In this slide, the Safeman's generalized transport equation is introduced. The Safeman's generalized transport equation is given in this form. Here, Q is the turbulence-related parameter, and A is the function of turbulence and the mean velocity. Nu D is the eddy diffusivity, or called the effective turbulence diffusivity. If we look at this equation, in the left-hand side are those local change and convective terms. These are consistent with the exact transport equation we have seen in the previous slides. And the first term in the right-hand side is corresponding to the production term, and the last term corresponding to the eddy viscous term, and the diffusivity coefficient can be regarded as the sum of the molecular viscosity and the eddy viscosity. Based on the generalized transport equation, Safeman could formulate his K-omega model. It should be noted, Safeman's transport equation is 4 omega squared, and this K-omega turbulence model has evolved to a very successful K-omega turbulence model of modern form. In fact, Kolmogorov formulated a similar K-omega model earlier in 1941, but his work in Russian was not known outside the former Soviet Union until much later time. Please see the information in the reference 2. London and Sharma in 1974 refined and tuned the K-epsilon model, which was generally accepted as the standard K-epsilon model. The transport equation for the kinetic energy K is given by the standard transport equation. And the transport equation for the dissipation rate epsilon is formulated as this. If we compare these two transport equations, we can see the transport equation for the dissipation rate can be basically derived from the transport equation for the kinetic energy by multiplying epsilon divided by K and adjusting the corresponding coefficient C epsilon 1 and C epsilon 2, etc. So this analog form is employed in most two-equation turbulence models. One question that also has in the exact transport equation for the dissipation rate, we have the exact production term given in this. But the constructed transport equation for the dissipation rate epsilon is different. Why? The kinetic eddy viscosity is calculated as this formula. So this relation is basically established on the dimensional analysis. A question may be asked, why the turbulence eddy viscosity µt is only related to K and epsilon? So based on the dimensional analysis, we can see the unit for the eddy viscosity. The unit is meter squared per second. And the kinetic energy, the unit is meter squared per second squared. And the dissipation rate, the unit is meter squared per second cubic. So if we make the analysis on the unit, we can see K squared divided by epsilon. We have the unit same as the eddy viscosity, meters squared per second. So for the standard K-epsilon model, the closure coefficient, and we also have two auxiliary relations given as this. The auxiliary relations are not necessary for the K-epsilon model itself, but it could provide the links of the model with the K-omega model and the Prandtl's one equation model. Selfman independently developed a K-omega model in 1970, which was inherited by Navier-Stokes and had been constantly improved by Navier-Stokes and many others. Following is the Navier-Stokes 2006 K-omega model. The transport equation for the turbulence kinetic energy K is given by this form. And here we can see the dissipation rate epsilon is replaced by the expression as this. And the transport equation for the turbulent frequency omega is given as this. So from these two transport equations, again we can see this transport equation for the turbulence frequency omega can be derived from the transport equation for K by multiplying omega divided by K and with the adjusted corresponding coefficient alpha, beta, and etc. Here in the transport equation for turbulent frequency, the closed diffusion term is added. This term is used to solve the problem of the free stream dependency, and this closed diffusion term can be understood to resemble the mentor's blending function in his SST K-omega model. The kinematic eddy viscosity is calculated as this mu t equals k divided by omega tilde. The parameter omega is given by this limiter. So this limiter could limit the magnitude of the eddy viscosity. Hence, it could greatly improve the incompressible and transonic flow prediction. The closure coefficient and the auxiliary relations are given here. And here, sigma d is a function similar to the Mentos blending function. So as we know, in understanding the fluid turbulence, two important parameters, the turbulence length scale L and the turbulence time scale tau, are frequently referred to. Therefore, it would be a natural choice that the two-equation turbulence model are constructed based on these two parameters. So this includes the Rota KKL model, which was proposed in 1968. This model basically extended the Prandtl's one-equation model. The transport equation for the turbulence kinetic energy K is the same as the transport equation in the Prandtl's one-equation model. Here we can see the dissipation rate epsilon is replaced by the Prandtl's hypothesis as this, and the transport equation for the parameter KL is given as this. So using this equation, the turbulent length scale L can be solved from this transport equation, rather than specifying the length scale as in the Prandtl's one-equation turbulence model, because specifying the turbulence length scale could be sometimes an impossible task, even for those experienced researchers. So the kinematic eddy viscosity is calculated with this formula, and the closure coefficients are given here. In 1986, Zierman and Wolfstein proposed the K-tau model. The transport equation for the turbulence kinetic energy is given by this, and the transport equation for the parameter K-tau is given by this. If we compare these two transport equations, we can see the transport equation for the parameter K-tau is very similar for the transport equation for the turbulent kinetic energy, multiplying the parameter tau and adjust the coefficient, here C tau 1, C tau 2, etc. The kinematic eddy viscosity is calculated in this formula, and the closure coefficients are given here, and also the auxiliary relations given here, which link the K-tau model to the K-epsilon, K-omega, and Prandtl's turbulence length scale. The first example is for turbulent boundary layer. From the theoretical derivation and the experiment data, it has been shown the log layer can be expressed as in this formula. Here, kappa 0.4 is von Karman constant, and C is a constant. And for the sublayer, y approaching to 0, we should have the asymptotic solutions to the parameter k, or for the expression this would be a constant. Based on the solution of the boundary layer using different turbulence models, it can be seen that the constant C can be well predicted using the K-omega model. But no turbulence model could predict the component N correctly when Y approaches to 0, and no model could reproduce the expression correctly, since all the predicted values are far from the measurement of the theoretical value. The second example is for the prediction of the spreading rate of the free shear flows. The definitions of the spreading rate for different flows are given in here. So in this table, we can see the prediction with the K-omega model, K-epsilon model, and the RNG K-epsilon model, which is an enhanced K-epsilon model. All these spreading rates are compared with the measurement value. So from the prediction, we can see the K-omega model gave the best answer to all this spreading rate. And in this table, we can also see that it is not necessarily the enhanced RNG K-epsilon model could predict the flows better than the standard K-epsilon model. This is understandable, since if the enhanced RNG K-epsilon model can predict all the flow better than the K-epsilon model, then the standard K-epsilon model would disappear. And in this table, more different turbulence models are compared. And again, the Navier-Stokes 2006 K-omega model gave the best prediction for the free shear flows. The third example is the backward-facing step flow. The comparison is made for two different top wall angles, alpha equals to 0 and alpha equals to 6 degrees. So the comparison using different turbulence model for the reattachment of the flow. You can see the one equation Spallard-Omelas model, K-omega model, and the K-omega K-epsilon model, the Mentos SST model, predict the attachment close to the experiment data. So if we calculate the error of the prediction compared to the measurement data, we can see for the top wall angle 0 degrees, K-epsilon model under predicted the attachment by 17%, and for the top wall angle 6 degrees, it under predicts the attachment by 32%. While for the K-omega model, the error is 7.7% and 4.3%. So from this example, we can see K-omega model is much better than the standard K-epsilon model. So in this slide, the summaries will be given for the conventional two-equation turbulence models, especially for the K-epsilon and the K-omega models. Basically, the two-equation turbulence models are complete in principle, but turbulence model will never be perfect in the author's opinion. They can only be used to solve some problems in the fluid dynamics, not all the problems. Therefore, the applicability to wide range flows is a key factor for all turbulence models. According to Mentor, how to construct the kinematic eddy viscosity is a critical factor for a successful turbulence modeling. The K-epsilon model was the most widely used two-equation turbulence model before 1990s. The reason why the K-epsilon model has been the most widely used two-equation model, it might be for the transport equation of the dissipation rate, because it is derived from the Navier-Stokes equation directly. But it is very complicated. Thus, many terms of it must be modeled or approximated. The K-epsilon model is extremely difficult to integrate through the viscous subrayer and requires viscous correction. The application successfully to some flows, but it is difficult for the flows with the adverse pressure gradient and for the separated flows. The K-epsilon model might need to be fine-tuned for a given application. For the K-omega model, now it has become the most widely used two-equation turbulence model, according to Navier-Stokes. The transport equation for the turbulence frequency omega is not derived from the Navier-Stokes equation, which is purely based on the physical reasoning and from the Selfman's generalized transport equation. The K-omega model is significantly more accurate for two-dimensional boundary layer with both adverse and favorable pressure gradients. The model can be easily integrated through the viscous subrayer. The K-omega model accurately reproduces the subtle features of turbulence kinetic energy behavior close to the solid boundary condition. The earlier K-omega model has a strong free stream dependency.